Welcome to this video on actin polymerization. Here we see an actin monomer with the positive end and negative end highlighted. The positive end of the actin monomer has higher affinity for other actin monomers, and this is important for the polymerization process. The initiation process of actin polymerization is called nucleation. In this video, we're showcasing this through the spire molecule. The spire molecule binds 4 actin monomers in a single strand that can then act as a template for other monomers to bind to, and so the polymerization process can begin. Here we showcase the positive and negative end of the monomers, and because they bind in this polarizing fashion throughout the entire filament, it gives rise to a positive and a negative end of the filament as a whole. And as a result of this, the positive end of the filament will polymerize more rapidly than the negative end. And also, the concentration needed for polymerization in both ends will be different, thanks to the difference in affinity. The concentration needs to be higher at the negative end for polymerization to take place, and this is illustrated in this example. So in this example, the concentration is right for both ends in the beginning, but suddenly the concentration at the negative end is not enough anymore, and as a result, polymerization will only take place at the positive end. And so the positive end will continue to bind monomers from this concentration pool, while the negative end will start to depolymerize. And so as a result, the negative end will keep providing the concentration pool with monomers that the positive end can bind. And this gives rise to a treadmilling effect, where the positive end will continue to polymerize while the negative end depolymerizes. And as you can see, the actin filaments moves as a result of this. And this is an important ability for the actin filaments, and it plays a role in a few functions. But before we take a look at that, we need to account for one more thing. The actin monomers can be bound to either ATP or ADP, and ATP-bound monomers have a higher affinity for each other. So ATP-bound monomers will bind at a higher frequency to the actin filament. And over time, these ATP molecules will be converted to ADP. And so at the negative end, there's a higher frequency of ADP-bound monomers which have a lower affinity for each other. Now lastly, let's take a look at a molecule that converts ADP-bound monomers to ATP-bound monomers. This molecule is called profilin, and it binds to the monomers and converts ADP to ATP. And on the other hand, we have molecules called ADF-cofilin. They bind to ADP-bound monomers at the negative end and cause a conformational change and a rapid depolarization of the negative end. Profilin can then come and turn these to ATP-bound monomers and make them able to assist in the polymerization at the positive end again. Now it's time for a quick recap. On the right we have ATP bound and on the left we have ADP bound monomers. And as we know, monomers from the minus end will bind to the positive end through treadmilling. And we have a few molecules that control the ATP and ADP conversion. First we have profilin that binds to ADP bound monomers and turn them into ATP bound monomers. And lastly, we have cofilin that binds to a big chunk of ADP-bound monomers, cause a conformational change and a rapid depolymerization. Lastly, let's take a look at one example of a function of this treadmilling process within the cell. One big function of this is to allow the cell to move. This is done by having the actin filaments treadmill towards a specific direction. And that was everything in this video. I hope you learned something.